we did common emitter characteristics. We plotted the input-output characteristics of the common emitter, right? So all of you finished any pending experiments? If you keep pending experiments, please inform me. Please try to get the output, and if any problem, you have to report to me. Don't say that finally I have not done this experiment, so I have not included in the report. So I'm assuming that all of you are doing this experiment and getting the output. So in case of any problem, please inform me prior.
Okay, sir.
Right. So shall we go to the next experiment?
Yes, sir.
Okay. Our today's experiment is common emitter amplifier. So last class we verified the characteristics of common emitter characteristics in LT Spice, and we plotted the input characteristics and output characteristics of the common emitter. So in today's class, so what is the application of transistor? What is the application of what is the use of transistor in the electronics? Any idea? To amplify the weak signal. Suppose you are addressing you are using a public address system, and you are talking through microphone. So what is the output of microphone? See, the microphone converts the acoustic pressure into electric signal, right? Electrical signal, right? Microphone converts the acoustic pressure into a electrical signal. So the output of is a kind of sensor. So the output of the microphone is a electrical signal. So what is the range of output voltage? Do you have any idea about the? So microphone output will be in the order of millivolts or microvolts. Very low, right? So this acoustic pressure is converted to electrical signal, and the electrical signal, electrical quantity is very low, very feeble. It is not enough to drive the speakers. So what is required to drive the speakers? You require some amplifier. So my output is in the order of millivolts. I need to amplify this to a sufficient level so that it can drive the speakers. So that is a basic requirement. So we use this transistor device for amplification. So what is the terminals of transistor? Transistor basically consists of two N regions. Two N regions separated by a thin layer of P region, right? Two N regions separated by a thin layer of P region. That is called NPN. For a PNP, two P region separated by a one N region. So that is a basic construction of the transistor. And so what are the terminals of transistor? What are the terminals of transistor? What is the name of the terminals? Electrical connections.
Emitter and collector.
Emitter, collector, and what is the other one?
Base.
Base. So it has three terminals, namely emitter, base, collector. And there are two types of transistor. Emitter, that is PNP transistor, and NPN transistor. So NPN transistor is most widely used than PNP transistors in most of the applications. And so what is the basic action of transistor? How will you operate the transistor? So you need to forward bias the input side and forward bias the output side. It has two junctions. Transistor has two junctions. One is known as emitter base and the other one is known as collector base. So it has two junctions, and charge, the current is carried by both electron and holes. That's why the name bipolar junction transistor. And so we have the terminals emitter base collector, and the emitter base terminal is forward biased. So you can see the diagram. So this is the transistor symbol, circuit symbol of the transistor. One is PNP, the other one is NPN transistor. So here the input junctions are forward biased, output junctions are reverse biased. So the majority carriers diffuse into the N region, and very few majority carriers are attracted by the N region, and majority of the carriers reach the collector terminal. So the collector has the negative potential, so it attracts the holes coming from the emitter. Majority carriers in emitter is holes, cuts the PNP transistor, and holes are attracted by the negative potential, and so the collector current is much greater than the base current, and collector current is dependent on the base current. The amount of collector current is based on the base current. So the large collector current is controlled by the small base current. So this is how the transistor amplifies the weak signal. And for amplification, you require the input junction must be forward biased, should be forward biased, and output junction must be reverse biased, right? And this is the basic circuit connection of the transistor bias voltages. And if you write the KVL across the output loop and input loop, you will get the set of equations. This can be easily obtained. And the last class we did this input characteristics, output characteristics of transistor. So we observed that on increasing the base current, the collector current is also increased. So this is IB0, IB1, IB2, IB3, and so on. So for every increase in the base current, there is a corresponding increase in the collector current. So IC is directly proportional to IB. So small variations in the input side is produces large variations in the output side. So that is the basic action of transistor. I think most of you are clear with the basic idea of transistor, and normally we use this type of biasing arrangements. So this is known as voltage divided bias. What is the specialty in this voltage divided bias? Why you need to actually you require how many sources for biasing? How many sources for biasing? Can anyone please? How many sources required for biasing? How many sources are required?
So
Two sources, but in this case, voltage divided by S has how many sources? Diagram is shown. Huh?
one.
How many sources? We have only one source, VCC, right? So this is known as VCC, and so here this is NPN transistor NPN. So the collector is reverse biased by the VCC, and base is forward biased by the same VCC. So single power supply, using a single power supply, it is possible to forward bias the input junction and reverse bias the output junction, right? So this is the basic advantage of voltage divided bias. This biasing is known as voltage divided bias. And so the base voltage is R2 by R1 plus R2, and V emitter voltage is VB minus 0.7 volt, because voltage across emitter is VB minus 0.7. 0.7 is the breakdown voltage of the transistor. So can you calculate the values of for the circuit? VB, VE, VC, IVC, IB, IC, and IC. And beta DC is given. What is the relation between beta DC? IC is equal to beta DC IB. So do this calculation for a while and I'll tell you. Working. Working on this or not? Yes, tell me.
Just a minute, sir.
Okay, okay. Found. Got it? Yes, got it? We can find the values directly by using the Kirchhoff voltage law and current law, and you'll get this value. VB is the voltage across R2, which is R2 divided by R1 plus R2 into VCC, voltage divider rule. So you will get 9.38, and VE is the emitter voltage, which is equal to V minus 0.7. 0.7 is the voltage up. And similarly, IE V by RE, I 8.68, and IC is equal to I for alpha DC is equal to 1, and IB is equal to beta DC. IC is equal to beta DC IB. So IB is equal to IC by beta, and you get and you can easily simplify this circuit, and you can find the values directly for the given values of resistor. So this is a basic arrangement of biasing of a transistor.
Sir,
Yes.
sir, from where base current will flow, sir? Exactly.
Base current.
Yes, sir. From VCC, it will divide to R1 and RC.
Yes, VCC. See, the point here is we have to make the collector emitter junction forward bias. That is achieved by the same VCC. Similarly, we need to reverse forward bias the input junction. So here the base is what type of material? It is NPN. So the base is connected to the positive supply, so it is forward biased. And so the current will flow through this resistor R1 to the base.
Okay, so that will be the base current.
Yes.
So from R1 in that junction, the current will again divide to R2 now, sir.
So base current is normally IC by beta DC. IC by B. This is the base current. Okay. Vila, what is your question actually?
From where base current will flow, sir? Direction, I want direction.
Direction. Direction of the base current. You can assume the current direction based on the current will flow from higher potential to lower potential. So based on that, you can assume the direction of current, right? Yes or no?
Okay. Yes, sir. Yes.
Okay. So that is a basic higher potential to lower potential. So from this, you can mark the current direction. So we can find the values of voltages and currents using the KVL, Kirchhoff voltage law. And you have to know the relation between IC and IB. So IC is equal to beta DC IB. So what is beta DC? Beta DC is the gain amplification factor, which is 200, is given in the question. So from this, we have calculated the current IB, and we also found the expression for VC. So by writing, so VC is equal to VCC. If you write a KVL, VCC minus ICRC, right? So this is collector voltage. This is collector voltage. If you so VCC minus ICRC is the, if you apply a KVL around this loop, you will get this equation, VCC minus ICRC. So what will happen? So input junction is forward bias, output junction is reverse bias, right? So for positive rising, for positive cycle, IC will increase in the positive direction or increase in the reverse direction. for positive cycle of the input. Let us assume that input signal is a sine wave. So for positive cycle, IC will increase or decrease?
Increase.
Say IC is proportional to IC increases. And what happens to, so if IC increases, the more drop across the resistance RC and VCE decreases. So you can. So why I'm asking this question is, so if you apply a signal to the voltage divided bias, and you can see that output signal is phase reversal of the input. And so we have a coupling capacitor and bypass capacitor. I'll show you the exact arrangement now. And this is the exact arrangement of the common emitter amplifier. So input coupling capacitor, output coupling capacitor, and bypass capacitor. And so bypass capacitor bypasses the AC signal. Because if there is an AC signal in the emitter, it will disturb the Q point biasing arrangement of the transistor. So to avoid that, we use a bypass capacitor. So it bypasses the AC signal because reactance value for high frequency is what? Reactance value increase or decrease?
For capacitor, sir.
Capacitor, yes.
Decrease.
Decrease. So the current will flow through the capacitor. So it will not disturb the emitter bias emitter voltage. So we need to have bypass capacitor, coupling capacitor. So this is the basic arrangement of the common emitter amplifier. So we have taken a simple common emitter transistor, common emitter amplifier, and we have removed the one source. We need actually two sources, and we removed the one source using voltage divided bias. And for AC signal operation, you require this input coupling capacitor, output coupling capacitor, and bypass capacitor. So that the operation of this amplifier will be taught in the class. So there will be there is a separate module for this theory. So no need to bother about the. We are going to basically test the amplifier circuit in the lab. So the theory will be discussed in the class. So no need to bother about the theory. I'm just explaining the use of bypass capacitor and output coupling capacitor, input coupling capacitor. So this is a basic arrangement. So, yes.
This will be which experiment in VLabs, sir?
Not in VLabs. We are going to do in LT Spice. VLab only for voltage regulator, Zener diode. See, last class we did in LT Spice only, transistor characteristics. Yes or no? What about others? Last class, what tool we used? Anyone, please? What tool we used in the last class?
Sir, both, sir. First VLab, then
VLabs and LT Spice. Yes, yes. VLab only for the basic understanding, and VLab only for the basic understanding. Actually, we need to do this in the LT Spice. So construct this circuit in the LT Spice now. Can you construct the circuit in LT Spice? Yes or no?
Yes, sir.
So I'll give you 10 minutes time first to finish the circuit. Circuit is done.
Yes, sir.
So next we are going to simulate this in the LT Spice. I'm now switch to LT Spice. So are you able to see the circuit now clearly? Circuit is made like this. All of you finished these connections? Yes or no?
Yes, sir.
Okay, next I'm going to simulate this. At this time, I'm going to simulate it. So which analysis I have to use for seeing the waveforms, input voltage, output voltage waveforms? Which analysis I have to use? Which analysis?
Transient.
Transient. So go to transient. Stop time. Let us give 100 milliseconds. Okay. So this is the input, 10 millivolt, and this is the output. So input is 10 millivolt, output is V03. We got the waveform like this. Yes or no?
Yes, sir.
So this is the output waveform. So you can see the amplification. Input is actually 10 millivolt. So here the green curve indicates the input waveform and blue one is the output waveform. So the input is 10 millivolt. 1 second, I'll show this. So this is the input and green is the input, blue is the output. So input is 10 millivolt, output is somewhat 350 millivolt, right? Peak to peak is 750 millivolt. So you can also see the phase reversal in the output waveform. I told this earlier. In common emitter transient amplifier, there is a phase reversal in the output waveform. So there is a phase difference of 180 degree between the input and output waveform. All of you have done this? Yes or no?
So for the VN4, I'm getting straight line, like zero only, but straight line, proper straight line.
You have to set the input voltage properly. I'll tell you. So,
Sir, can you also show how to place that emitter, sir?
okay, I'll show you. So this is a circuit connection. Which is what is the doubt? What is your doubt?
Sir, once can you remove and place the emitter, sir?
Emitter. I'll remove the transistor now. So once again, I'm NPN PN. So place it like this and then go to the transistor part. Pick new transistor. So 5, what is the number of the transistor? 5, what is the number? 547B. Okay.
Yes, sir.
So all of you constructed the circuit and verified the output, input output waveforms.
Yes, sir.
Next, we are going to plot the bandwidth of the amplifier. What is the bandwidth? How will you calculate the bandwidth? So you have to plot the frequency response of the amplifier, right? For bandwidth calculation. See, we plotted the frequency response of a band pass filter. So how the bandwidth is calculated in the band pass filter? How the bandwidth is calculated?
So difference of the frequency ranges.
Yes, higher cutoff frequency minus lower cutoff frequency. So what analysis we need to use for bandwidth calculation? What analysis we need to use?
AC sweep.
AC? AC sweep, AC analysis.
Yes, sir.
Uh, So go to AC analysis, simulate edit simulation. So AC analysis, type of sweep is decade and start frequency is 10 milliseconds and stop frequency is 10 gigahertz. For 10 gigahertz. Settings are given. Now we can plot the frequency response of the amplifier. So simulate it. Are you getting the bandwidth? Number of points. Okay, simulation settings. Simulation settings, start frequency 100, 110 hertz. Yes, now it's somewhat clear. Are you getting this waveform? Bandwidth. So this is the frequency response. This is the phase response. So you can see the phase variations of the output. And this is the frequency magnitude response of the amplifier. Plotted this waveform, all of you?
Yes, sir.
So now how will you calculate the bandwidth for this? So you have to find 3 dB line, right? So the highest frequency here is 30, 30, 37, 37, 30, 37. So 37 minus 3 is 35, right? So place the cursor in 35. So what is the what is the exact x-axis? It's 256.77, right? 256.7 hertz. So this is F1. This is F1. And similarly, F2 is 96 point. F2 is 90. That is 101.2 megahertz. So F2 minus F1 is the bandwidth. So what is the bandwidth of the amplifier? What is the bandwidth? Anyone, please?
Sir, I'm getting a bit different graph. Can you please show that AC sweep data we have entered?
Yes, yes. Okay, I'll show you the settings. Settings are done. Everyone got it? Everyone got it?
Yes, sir.
So this is the output graph bandwidth, and so we have plotted the transient response as well as the frequency response of the amplifier. So the frequency response plays an important role because you can see from this diagram the gain drops in the lower frequency range and also in the higher frequency range. So this is the ideal. So this is the bandwidth of the amplifier. So gain drops in the low frequency as well as in the high frequency range, and this is for the if we don't use the capacitor. So what will happen? Let us see.
Sir, I have shared the image of my graph in the chat. Can you please check what I have done wrong?
Yes, you have to change the settings. Settings are not correct. I'll show you the settings now.
Sir, I have done that also. Still, it is showing me wrong.
Decade, right?
Yes, sir.
Number of points per decade is 100.
Yes, sir.
Start frequency is 10. Stop frequency is 10
Yes, sir.
gigahertz. And close it. Then again run. If you want, you can disconnect the
Yeah, sir, it is running now.
Got the correct waveform?
Yes, sir.
Okay. So this is the output waveform of the this frequency response of the common emitter amplifier. Now I'm going to remove this capacitor. Let us see the effect of removing the capacitor, bypass capacitor.
Sir, here how to measure the bandwidth? Sir?
Bandwidth is you have to see the highest frequency, highest gain. So the highest gain is 37.9, right? Highest gain is 37.944, right?
Yes, sir.
And minus 3 dB. Minus 3 dB is how much? Somewhat around 35.9. 35.9. Okay, this is the point, 284 hertz. This is F1. And F2 is 35.9. So it's 109.191 megahertz. So subtracting this higher frequency, subtracting the lower frequency from higher frequency, you get the bandwidth. Fine.
Yes, sir.
So let us see the effects of suppose if I apply suppose if I change this to 100 millivolt, 10 millivolt, I am applying 100 millivolt. Will it effectively amplify this signal 100 millivolt? Let us see. So run the simulation and go to the edit transient analysis. Stop time is 10 milliseconds. Okay. Now I am connecting the input. Okay, I'm going first. I need to close this. Edit simulation setting. Transient analysis. Okay. Next run this. So input is 10 millivolt. So you can see the output is somewhat distorted. I'll show you the correct graph now. Edit simulation. Stop time 100 milliseconds. Could you see the difference for 10 millivolt and 100 millivolt? Yes or no?
Yes, sir.
So it's a faithful reproduction or not faithful reproduction? Amplifier has to faithfully reproduce the signal, right? Waveform should not be distorted. So here, but if you increase the input voltage to some 100 millivolt, the output waveform is distorted. Transistor cannot amplify the signal. So that's why you have to choose the proper biasing. So for example, if I increase this power supply voltage to 25 or somewhat right, okay, right? If I increase this to 23, so you have to choose the proper value Q point for proper operation of the transistor amplifier. Otherwise, output waveform will be distorted. So 15. So I'm 15. This is 10 millivolt. Okay. Now I'll get the correct waveform. So let us see what will happen if capacitor is removed. So capacitor is removed now. Gain increases or decreases? Gain increases or decreases from the waveform? Increases or decreases?
Decrease.
Decreases. So bypass capacitor plays an important role in the transistor amplifier. So without bypass capacitor, the gain, you can't achieve the desired gain. I'm placing this capacitor. $200 micro. So when you design a transistor, you have to look into this Q point of the transistor. What is Q point? What is the Q point? Operating point. So anyway, I don't want to ask any questions. Next, we will do the circuit. Next application of transistor is the switch, right? Shall we do switch operation? Okay. New schematic. So go to new schematic. New schematic, and this is the circuit diagram for a switch. What is switch transistor? How transistor acts as a switch? See, this is the basic circuit of switch. So switch means it performs the inverter. So the input is 5 volt, output is 0 volt. Input is 0 volt, output is 5 volt. Inverter, not gate. So we can realize non-gate using a simple transistor circuit like this. So can you design this circuit RC 1 kilo ohm, RB 22 kilo ohm, VCC of 5 volt. So kind of construct this circuit, verify the switching operation. So VB is greater than 5 volt, 6 volt means what is my output? When the input is high, 5 volt, output is what? Somewhat 0.2 volt. And similarly, when the input is, so construct this circuit now. So you require a transistor for switch. Let's take NPN transistor and connect this single wire. What is the power supply voltage? What is the power supply voltage? 5 volt, right? Connect power supply. Power supply voltage is 5 volt. Voltage you require one more source. Input voltage. Voltage. Where the circuit is connected. Let us use ideal transistor. Otherwise, so what are the values? 1 kilo ohm, RC 1 kilo ohm, RB is 22 kilo ohm. This is 1 kilo ohm. This is 22 kilo ohm. And this is 5 volt. And let us see the output for 0.3. So what is my output? What should be my output for 0.3? 0.3, what is the output? Transistor is forward biased or reverse biased? Input junction is forward biased or reverse biased? That is emitter base junction is forward biased or reverse biased? Input junction is reverse biased, right? That is
Reverse.
yes, because it should exceed 0.7 to overcome the potential barrier. So 0.3 is so you can't. So the input junction is reverse bias. So what is my output? Transistor acts as an open switch. So what is the output? As same as 5 volt. So I will check the output. So edit, simulate, then simulate it. Do the transient DCC. Transient. Yes, agreed. So for 0.3, for low input, output is high. Similarly, if you increase the output input to 0.8, what is my output? What should be my output? 0.8 for 0.8. What is the output for 0.8? Anyone, please? Point 0.8 input junction is forward bias. So it acts as a closed switch. So output is 0. Okay, the put resistance value. Okay, 2 volt. Let's see, 2 volt. Showing 4.9. Five, 5 volt. So you could see the millivolt now. So for binary 0, output is binary 1. For binary 1, output is binary 0. So this is the basic transistor acting as a switch. Any questions in this? So I'll give you 5 minutes time. You do this. I'll take attendance at 1:10. So do this, and if you face any problem, call me.
Sir, how to get millivolts, sir?
Huh? How to get?
How to get millivolts, sir?
View all. What is you are asking?
How to get millivolts, sir? Millivolts.
Millivolt. Millivolt, it automatically will come. See, for binary, this is input is 5 now. So it represents binary 1. Output is should be 0 for NOT gate. So 0 means it's 93.3 millivolt. Have you done this experiment? Switch, transistor switch, verify the output for both cases. Have you done this experiment or not?
1 minute, sir.
So I'll give you the list of experiments in Teams. So maintain this report accordingly. So first experiment is band pass filter. Band pass. Second experiment is diode characteristics. Diode characteristics. Second A. Second A is diode characteristics. And A. Diode characteristics. And second D. Second B is rectifiers. And third is what was the third experiment? Common emitter, right? Zener diode. Zener diode.
I guess line rectifier.
Huh?
Line rectifiers and load rectifiers.
Time?
Line rectifier and load rectifier.
A line regulation, load regulation. The fourth one is common emitter. And fifth is CE amplifier. So I've given the list of experiments done so far. So based on this five experiments, you prepare the report and I'll create a link and upload it. Okay. Now it's clear what experiments we have done so far.
Yes, sir.
Sir will submit it after Cat 1, right?
Yes, you can submit after Cat 1. So all of you have completed all the 5. Please do it, and if any problem, you can ask the teaching assistant also. They'll be ready to help you.
Sir, do we directly message you in Teams, sir, if we have doubt?
Yeah, Moodle. I'll create a link in Moodle. You have to upload only in Moodle, not in Teams.
No, sir, I'm saying if we have a doubt, sir, to contact you.
You can contact me. You can type message in chat box and you can get clarification. Or okay, during the class, better to ask questions in the class because I can easily. I will be free and I can explain. So we have 2 hours class. So LT Spice doing a experiment in LT Spice takes only half an hour. So rest of the time we are just doing some calculations and so we can utilize the time for your doubts. So anything else? Now it's clear with the list of experiments. Okay. I'll upload the PPTs also. Some of the PPTs required for preparation. So I'm not uploaded so far. I'll upload it. So all of you please stay. I'll take attendance now.
Sir, can you upload in MS Teams?
MS Teams only. There is no other platform. They are not having any WhatsApp group. All of you give your attendance. Please get back. Please get back to L23, right?
Yes, sir.
So please
Yes,
answer.
sir.
Amsika
Present, sir.
and Naman Kumar.
Present, sir.
1 second. Naman Kumar,
Yes, sir.
Vivin,
Yes, sir.
Gokul Krishna,
Present, sir.
Giridhar Prakash,
Present, sir.
Shahid Ahmad,
Present, sir.
Ankita Das,
Present, sir.
Priyanshu Bansal,
Present, sir.
Aditya Sharma,
Present, sir.
Abdul,
Present, sir.
Tejas,
Present, sir.
Pranav, Harish,
Yes, sir.
Nitin Reddy, Shivashankar,
Present, sir.
Rohit Chaudhary,
Present, sir.
present, sir.
Hariharan,
Present, sir.
Amal Vishnu,
Present, sir.
Ishan Saxena,
Present, sir.
Krishna Chaitanya,
Present, sir.
Suresh,
Present, sir.
Lauren,
Present, sir.
Vishweshwar Reddy,
Present, sir.
Sanchana,
Present, sir.
Abhirami Bhaskar,
Present, sir.
Venkata Yogita,
Present, sir.
Ashit Kumar, Ashit
Present, sir.
Srinidhi,
Present, sir.
Jiva,
Present, sir.
Abhigyan,
Present, sir.
Yedu Krishnan,
Present, sir.
Rahul,
Present, sir.
and Vikram Aditya,
Present, sir.
Suprato Dey,
Present, sir.
Sanjay,
Present, sir.
Sai Venkatesh,
Present, sir.
Ankit Singha,
Present,
Ankit.
sir. Present, sir.
Kritika,
Present, sir.
Sriram,
Present, sir.
Bhavya Yadav,
Yes, sir.
Rishikesh,
Present, sir.
Manmeet Singh,
Present, sir.
Siddharth,
Present, sir.
Nikunj Agarwal,
Present, sir.
Dhananjay Reddy. Okay, Charan Rahul,
Present,
Charan,
sir.
Kirat Singh,
Present, sir.
Devansh Gupta, Devanathan,
Present, sir. Present, sir.
Sanjupta,
Present, sir.
Sir, Rahul Prem present, sir.
Rangaraj,
Present, sir.
Stanley,
Sir, Freddy, present, sir.
Freddy. Okay, Megha Viga,
Present, sir.
Rishwant,
Present, sir.
Deepan,
Present, sir.
Gopinath,
Present, sir.
Gopika,
Present, sir.
Jervin Matthew,
Present, sir.
Mohammad Salman,
Present, sir.
Harsh Dev Narayan Singh, Harshdev, Gokul Raj,
Present, sir.
Neha,
Present, sir.
Surya Deepan,
Present, sir.
Guru Prashant,
Present, sir.
Mohammad Azim,
Present, sir.
Sindhu, Kapilan,
Present, sir.
Nitin,
Present, sir.
Maurya,
Present, sir.
Satyajit,
Present, sir.
Chantak Das.
Present, sir.
Okay. So I'm going to close the attendance now. Only the absentees, Sidhu, Sidhu only. Sidhu and yes,
She sent a message in Teams chat, sir.
Sidhu.
Yes, sir. Her mic is not working.
Okay, submitted. Okay, given present. So all of you can leave. Any questions?
Sir,
Any questions?
sir, so can you hear me?
Yes, yes. Tell me.
For the first one, band pass, which manual should we write from VLab, sir?
In a man pass filter, I'll give the material.
Okay, so rest of all the other experiment we have to take from VLab.
Yes. Band pass filter, I'll give the. You can refer some books, or I'll give you the. You have the circuit diagram, right?
Yes, sir, but not the manual things like.
Manual.
procedure.
You can also create manuals. See, you have the circuit diagram, you have the results, and this description can be found from the any sites. Say, and formulas also can be found. Anyway, I'll upload the slide for band pass filter.
Sir, we can just create a Word document, sir. Is it necessary to write it?
The Word document is sufficient. You have to copy paste the LT Spice circuit diagram, LT Spice result.
Okay, sir.
Other things you can write. You can type.
Okay, thank you, sir.
Only for serial diode voltage regulator we used VLabs. So rest of the experiments are done in the LT Spice only.
And BJT also, sir. We use VLabs.
Yeah, BJT. Now only to learn some basics in VLabs. We verified the output only in LT Spice one. The CATSI graph we plotted only in LT Spice.
Sir, should we show the calculations or can we just paste the table from VLabs?
Yes, you can paste the tables from the VLab.
Okay, sir.
So no questions means I'll close. So all of you, thank you.
Thank you, sir. Have a good day.
Thank you,
sir.
Thank you, sir. Thanks.
Thank you, sir.
Thank you all.
Thank you, sir.